which is how to use radicals. Okay. So today we're going to learn how to add or we're going to review or learn how to add and subtract radicals. We're going to learn how to simplify radicals. We're going to multiply radicals, multiply binomials, and we are going to stop there because day 2 is rationalizing the denominator. Okay, something, again, more new words, right? Notice this course has so many new ideas and words. All right, so we're going to use the term like radicals, and that's like collecting like terms. Remember when we were collecting x squared because they were like terms? Well, a like radical is a radical that has the same radicand. So 3 root 2 and 2 root 2 are like radicals because they have the same radicand, the same number under the square root. If you have your telephone out, put it away. But away, like your bag away. Yes, excellent. Okay, so we know that we can add 3x and 2x, right? And that will give me 5x. And that is because they are like terms. So what really we're doing when we're adding those, we're actually common factoring, right? So when we have 3x and 2x, it's like I common factor out the x, and then I add what's left inside, okay? So the same thing can be done for radicals. So if I have 5 root 3 minus 2 root 3, what would be the common factor here? The root 3. And if I factor out the root 3, I'm left with 5 minus 2. And 5 minus 2 is 3, so I'm left with 3 root 3. Now, you do not have to solve problems this way. This is just to really break it down and show you why it is that identical radicands are like terms. Okay? So let's try an example. So in example 1, I've got 4 root 3 minus 5 root 3 plus 2 root 3. Okay, so I'm going to show the common factoring approach. So if I have a root 3, I've got 4 minus 5 plus 2. Right, 4 minus 5 is negative 1 plus 2 is positive 1, and that leaves me with root 3. Right? Of course, I could write 1 root 3, but that's the same as writing 1x, right? We don't write the 1. That coefficient is assumed. Now, again, you do not need to write your work this way. Okay, you can skip directly to the simplified version. Yes? Say it again. Oh, like a 2?
Yeah.
Like an index?
No, but if you just write the root, there's supposed to be 2 in front, right? So
Did I add there incorrect? I don't understand.
Whereas there's supposed to be 1.
Like that?
Yeah, but I'm saying if you leave it as root 3, you're saying you need 2 in front.
No. Okay, good question. Because here we're confusing the coefficient with the index. And the index is assumed to be a 2, and the coefficient is assumed to be a 1. Does that clear it up? But that's a great question, right? Do you see how that could get really confusing? We're assuming 2 things. There's a third thing we're assuming or not showing. It's the power. What is the power in this case? A 1, right? Again, we're not showing that. So 3 things that we're not writing, right? Because the final answer, the simplified answer, should look like this. All right. Now, before we do the second question, let's look at how we can simplify a radical by finding the perfect square factors. Now, before we do that, let's make a list of all the perfect squares we know. 1 squared equals 1. 2 squared, actually, other way around. Square root of 1 equals 1. Square root of what equals 2? Square root of what equals 3? Okay, write this down if this is not automatic. So what's the square root of what gives you 2? 4. 9. 16. 25. Beautiful. 36. 49. 64. 81. Let's keep going. For 10? For 11? 121. For 12? 144. For 13? 169. For 14? Ooh, that one, I don't know. Is it 184? I'm stuck there. So you get the idea, right? The more of these you know, the more automatic this becomes. Okay, so why is this going to be helpful? So what I'm going to do is I'm going to take a radicand of 12 and I'm going to break it up into smaller factors. 12 can be broken up into 4 and 3, right? Do you see this? And the reason why I did that is because the root of 4 times 3 can be written as root 4 times root 3. And root 4 has a perfect root. What is it? 2. So I can simplify root 12 to be 2 root 3. It's kind of like a mixed radical, right? We want to make the radicand as small as possible. That is simplification. So let's look at this question, at this example. We've got 2 root 27. So the 2 stays. Now 27, how can I break that down into smaller factors, one of which being a perfect square? Yeah. 9 times 3. And so that means that it's root 9 times root 3. Right? And that's times 2. And the square root of 9 is what? Yeah, so I've got 2 times 3 times root 3. Now I'm showing many steps here, right? Like this is something that you might be able to do in one step. And then I can multiply the coefficients. So 2 times 3 is 6 root 3. And so this is the simplified version because the radicand is the smallest it can be. We good? So let's take this and do the second example. Okay, so first thing I notice in example 2 is that all the radicands are different. So I can't combine them because they are not like terms. But I wonder if I can make some of them like terms. So let's see, do any of these have factors? Oh yeah. So 4 root 3 cannot be changed, right? Because 3 is a prime number. But 3 root 20 can be broken down. So 20, what can I multiply 20 by? Yeah. 5 and 4. And I just, in practice, always put the perfect square first. So I'll write 4 times 5. So that's a good question. Could I do 10 and 2? Can I take the square root of 10 or 2? I can't. So that wouldn't be helpful. Okay, how about 12? What can I break down 12 into? Yeah, 3 and, yeah. I'm going to write 4 first because it has a perfect square. And then the last one, plus 6. How about 45? Beautiful. Root 9 and root 5. Okay, so now I can take those square roots. 4 root 3 doesn't change. But in the orange expression, I can take the square root of 4. So I get 3 times 2 times root 5. Again, I'm showing a lot more steps that are than are necessary. In the light blue expression, root 4 is just 2, so I get 2 root 3. And in the pink expression, root 9 can be simplified to 3 root 5. Okay, so let's simplify further. Let's multiply the coefficients. 4 root 3 plus 6, whoops, minus 2 root 3 plus 18 root 5. And did this help me? Absolutely. Because now I have 2 pairs of like radicals, right? I've got these radicals, so I combine them. 4 minus 2 gives me 2 root 3. And then I have these like radicals that have identical radicands. 6 plus 18 is plus 24 root 5. And this is as far as I go, because the purpose of simplifying radicals is to reduce the radicand, to make the radicand as low as possible. Okay, let's try one more question. So that means we're not going to get to question 4, the FOIL one. So you might not do some of the homework questions. All right. Now, we can also multiply radicals, okay? And so when you do that, you multiply the 2 radicands. So if I have root 3, a monomial, times a binomial, I'll multiply 3 times root 6, right? So that's root 3 times root 6. Then I multiply root 3 times negative 1. Minus root 3. And so in this case, as long as the index is the same, you can actually multiply the 2 radicands. Okay, so the square root of 3 times the square root of 6 is the square root of 18. Do I stop there? No, because I can simplify root 18. I recognize that root 18 is also root 9 times root 2. Well, root 9 is 3 root 2 minus root 3. I cannot combine these 2 radicands. They're not like radicands, so I leave it. Now, let's take a look at your homework, okay, because we didn't get to let's just see when we're going to stop. homework. Here we go. All right, so you are going to go up to let's go fly a kite. Okay, you're not going to do question 5. I think up to question 4. Yeah, that's right. So today you're going to do questions 2 to 4. That's day 1. Okay, and day 2. Can we do that? Oh, and you can do 17, I think. 2, 4, and 17 on day 1. And day 2, you're going to do 5 to 7, 10, and 11. Folks, reminder today after school extra help. It's a different schedule. So if you need to write it on your hand or write a reminder to yourself to come to extra help, please do so. Okay, otherwise I will see you tomorrow.